Here are some tips for Lab 9, the iron unknown. The first thing you have to do on your post-lab is balance these two redox reactions in acidic condition. These are the two reactions that you're performing in this lab, and you need the stoichiometric coefficients for the reactants in order to be able to complete the data tables on your post-lab. Question number 3 has a data table that comes from the standardization of the potassium permanganate solution. In the first spot, you're going to be reporting the mass of the As2O3 solid that you used for each titration, and then you're going to convert that mass into moles. This is just going to be a straightforward gram to mole conversion using the mass and the molecular weight of As2O3 and converting that into moles. Then you are going to be converting the moles of As2O3 into moles of KMnO4. To do this, you are going to use the balanced equation in problem number 1, the first equation that you balanced. This balanced equation is going to give you the relationship between these two substances. This is unbalanced. It's not a one-to-one relationship, but once you get it balanced, you will know the relationship, so you'll be able to figure out the moles. So this is a mole to mole conversion. The next 3 spots, you'll be reporting your burette volumes, your initial burette, your final burette, and your total burette volume in milliliters. And then you'll convert this number here into liters. And then, last but not least, you can calculate the molarity of the potassium permanganate. Molarity is moles per liter of potassium permanganate. So you're going to use your moles of potassium permanganate and your volume in liters of potassium permanganate. That's going to give you this number right here. You've got 3 trials. These 3 titrations should be pretty similar to each other in terms of the molarity that you calculate down here at the end. They might have different masses, which means that they would have different volumes, but at the end, your molarity values should all be pretty consistent. Down here, you're going to calculate the average molarity to 4 decimal places, and then you'll be copying that on the next data table. The next data table has to do with the second titration that you performed. This is the test of the FeCl2 mixture. You'll be reporting initially just your burette volumes, your initial, your final, and your total burette volume, and then convert that total volume into liters. This is where you will report your average KMnO4 molarity. That's the average that you took right here in problem number 4. So you'll just copy that into all 3 of these boxes. You will use your average molarity and your total volume to calculate the moles of KMnO4. Remember, molarity is moles per liter. We are using the average molarity as the molarity in this equation, and your total volume in liters is your liters, so you'll be able to calculate moles. Once you get the moles calculated, you're going to do a mole to mole conversion using the balanced equation in problem number 2, the second equation that you balanced. The second equation gives you the relationship between FeCl2 and KMnO4. Let's go take a look at that. FeCl2, which is Fe2 plus in this equation, and MnO4 minus, which is KMnO4. So whatever the stoichiometric coefficients are for these 2 substances, that's what you're going to be using to convert KMnO4 into FeCl2. Once you get that calculated, you are going to do a mole to gram conversion. You're going to take your moles of FeCl2, use the molecular weight of FeCl2, and then convert that into grams. In this spot, this is where you will have reported the mass of the sample that you used in the titration. So the mass of the unknown FeCl2 substance that you weighed out at the very beginning of the titration. This number is definitely going to be bigger than this number right here. Remember, this unknown sample contains, in it, we have some FeCl2, but then we also have some impurity mixed in there as well. The titration allowed us to measure just the pure FeCl2. The titration ignored the mass of all this random impurity in there. So this mass is always going to be heavier than the mass of the pure FeCl2. And once you have that number copied down, then you can calculate the percent of pure FeCl2 in your sample. That is going to be the mass of the pure FeCl2, that's what you calculated from your titration data, divided by the mass of the unknown FeCl2 sample. Again, the mass of the pure FeCl2 is this number right here, the one that you calculated doing the mole to gram conversion. The mass of the unknown sample, that's the stuff that you weighed out. You are, last but not least, going to calculate the average percent FeCl2, so the average of all three of these, report it to 2 decimal places. These numbers, again, should all be pretty consistent with each other. Your masses may be different, have some variation, which means that your volumes would have some variations as well. But at the end of every one of these columns of data, your percent FeCl2 should be pretty consistent. Last but not least, make sure you upload a picture of your results after you type them into the software.